Welcome, ladies and gentlemen, to our lecture about forces and Newton's laws. So this is the point that we really start getting into some meat about physics and the way that the world works. It's at this point that we start to consider why things are happening. To this point, as we've looked at kinematics, we've just considered what objects are doing. Newton's laws starts to give us our first insight into why these objects are behaving in this way. And we have here on our front page a picture of Newton with his apocryphal apple, and we have a picture of a block sitting on a ramp that any physics student has probably seen a million times, but we'll come back to this diagram a little bit later. So let's start by talking about forces. Forces push or pull on objects. You apply a force to a car when you push it from behind. And gravity applies a force on you when it pulls you toward the center of the earth. Forces are interactions. In our example with you and the car, you push on the car. It's an interaction between you and the car. You're an object outside the car that applies what we call an external force to the car. Forces are also vectors. If we think about a push or a pull, it has both a magnitude and a direction. If we apply multiple forces from the same point, then the object will behave as if there's just one force, and that force will be a vector sum of the forces. So for example, if we have a block like this, and we pull on it from here with two ropes, we pull on this, and this is a vector, a force of one person pulling on it, and a force of a second person pulling on it. These vectors have a magnitude and a direction, and the way the block will behave when these two forces pull on it is as if there was just one force, and that force was equal to the sum of all of the other external forces acting on the object. So I want to teach you about forces today by teaching you about Newton's laws. Newton really made physics a thing with these laws, and they're still fundamental to the study of physics today. A thorough understanding of these laws is one of the most important takeaways that you should have from this course. So really try to internalize the concepts that these laws are considering. Really think about what these laws mean. Newton's laws are empirical laws of nature. Newton observed the results of experiments, both by himself and by other people, and he came up with these laws that describe the way that objects act in the physical world. As a physical law, what he's described here is a rule that objects always follow. So let's start, as one might guess, at the beginning with Newton's first law. So I said that forces push or pull on things, and I said that with multiple forces, the object will act like it has just one force on it. And that one force is the vector sum of all the forces that are acting on the object, or what we call the net force. Okay? So, net force equals the sum, this little sigma means sum, of all the forces acting on an object. And Newton's first law is very simple. It says that an object's velocity changes if and only if there is a net force acting on the object. So let's think about a really simple example. Imagine that we have a ball, like this basketball here, and we're holding it out at shoulder height. Okay? When we let it go, it falls to the ground. So it changes from standing still to having some velocity as it drops. You know from our prior lectures that, in fact, its velocity is changing the entire time that it's dropping because it has a constant acceleration, g. So if I draw the ball after I let it go, we think about this basketball after I let it go, I can approximate the system by saying that there's only gravity acting on the ball. That's what we've done by doing projectile motion, right? We've always assumed that once we let the object go, once we stop interacting with it, it only has gravity acting on it. There's only the force of gravity acting on the ball. So gravity is the attractive interaction between the earth and the ball. With only gravity acting on the ball, this is the complete system here. It's just the basketball with gravity pulling down on it. And with a net force on the ball, the net force is gravity pulling down, its velocity changes. But what was happening before we dropped the ball? We know that gravity was still acting on it, and we know that because we can feel it being pulled down by the earth. It has a weight. But to hold it up, we apply a force to it. We work against that gravitational force. And while we're holding it still, it has a velocity that's not changing, right? Specifically, it has a zero velocity that is not changing. So it's because we provide this force upward, the force of our hand, we'll say, that the velocity of the ball doesn't change. And this example illustrates Newton's first law of motion. An object's velocity changes if, and only if, there is a net force acting on it. When there was a net force of just gravity acting on the ball, the velocity changed. And when there was no net force, because the force of gravity on the ball was exactly balanced by the force of our hand, then the velocity did not change. That's Newton's first law. So we know now that Newton's first law tells us that an object's velocity changes when there's a net force on the object. But we might then ask, how does it change? If I do have a net force on an object, what does the change in velocity look like? So if we think about Newton's first law for a second, we could write that a net force, or the sum of all the forces, right? Net force is the sum of all the forces. And we could say that leads to a change in velocity. So that makes a change in velocity. But remember that when we're talking about velocity, we said that the rate of change of a velocity was an acceleration. So if we cause a change in velocity, there must be some rate to that change. So what we're actually causing is an acceleration. But how does the net force relate to the acceleration? So let's think about the example of you pushing a car again. If you've ever pushed a car before, you probably know that it can be really difficult. You push really hard, and it only barely makes the car move, right? But if you have pushed a car before, you may also have noticed that if you keep pushing on it, you can keep building up the car's speed, right? So you keep pushing really hard, and its speed only changes a little bit at a time, but if you keep pushing on it and keep pushing on it, you can build up more and more speed. And that's because as long as you keep providing a net force to the car, you keep imposing an acceleration on the car, which means that its velocity will continue to change. So as long as we provide this force back here, we give the car an acceleration, and that means that its velocity keeps going up. Okay? Or it keeps changing. In this case, it goes up, but you can imagine if it was already rolling and we pushed on the front, we could try to slow it down instead, so we could have the velocity go down. But in either case, there's an acceleration. So now let's engage in a little thought experiment. And a thought experiment is a physicist's word for navel gazing or daydreaming. And in our thought experiment, let's consider pushing two objects. And we're going to push them both as hard as we can. Okay? So let's first think about pushing a little child on a skateboard as hard as we can. If we think about that, you could probably give the child a pretty big speed in one big, hard push, okay? They probably have to sit on the skateboard so you don't knock them over. But you could probably push them one time in one big, hard push and give them a pretty big speed on the skateboard, okay? But now imagine that we do the same thing with a car. The car doesn't have the brakes on, it's just sitting there in neutral, so it can roll freely. But if we give a car that one big push as hard as we can, it barely rolls at all. So what's the difference there? In both cases, if we push as hard as we can, we apply about the same force. So what's the difference between these two things? Well, when you think about it, you probably know right away what the difference is. The car is huge, right? When I push something huge really hard, it barely moves. We know that. When I push something small with the same force, it moves really fast. Think about how fast you could throw a baseball versus how fast you could throw a bowling ball. The one that's much smaller, has a much smaller mass, you could throw really fast. And the other, with a much bigger mass, well, you can barely throw that one at all, right? So this gives us a relationship. The acceleration that a force of a given magnitude causes is inversely affected by the mass. So bigger masses have smaller accelerations when they're pushed with the same force. So experiment has shown that the relationship between acceleration and the net force looks like this. A is directly proportional to the net force and inversely proportional to the mass. Thinking about our car versus the child on the skateboard, if we can push with the same force here, then we get a different acceleration because the car probably has over 100 times the mass of the child. Okay, so this part is not equal. So with the same force, we get a different acceleration. So Newton's second law is most concisely conveyed by writing down this equation in a form that we usually write it. So this equation is usually written: the sum of the forces is equal to mass times acceleration. This is Newton's second law. And this equation is really the most fundamental equation in physics. And it's a powerful tool to put in our physics toolkit as we go forward in this class. The first thing to look at here, as always, is the units, okay? So if we look at the right side of the equation, we notice that we have kilogram, meter, per second squared. And the unit of force is named after the man himself. It's the Newton, abbreviated N. And 1 Newton is equal to 1 kilogram meter per second squared. Newton's second law gives us the definition of the units of force. So if you can't remember what the Newton breaks down into in these fundamental units, you can always remember F equals ma, and you can figure out immediately what the units of a Newton must be. So note that this equation is always true. It's true for each moment in time. So a force can only cause an acceleration while the two objects are interacting. You can only give a car an acceleration while you're pushing on it, while you and the car are interacting. Your push doesn't apply a force to the car once you let it go. So why then is gravity always present for objects on the surface of the Earth? So gravity is an interaction between objects that doesn't require them to be physically touching in the way that we normally think of the concept of touching. So at all times, an object near the Earth is interacting with the Earth through the force of gravity. Your book calls the push on the car a contact force, or a force that's acting while the two objects are touching. And it calls gravity a long-range force, or one that works while there's empty space between objects. These are two different kinds of forces, but in both cases, the force is applied only while two objects are interacting. So before we move on, I want to look at one more thing about forces and this equation F equals ma. So consider the car just sitting here. We know that gravity is always acting on it, so we know that we always have the force of gravity going this way. But we know that it's not falling. And we know the reason it isn't falling is because the ground is in the way. You can imagine if I scooped out the ground right here, the car would then drop, right? If I could instantaneously scoop out this ground, the car would then drop down to the bottom of the hole. But the car's velocity isn't changing when it's just sitting here. And we know that if the velocity isn't changing, there must be no net force on it. And that's because the ground is pushing back up on the car. And we call this force from the ground the normal force. The normal force always acts perpendicular to a surface. Okay, the normal force comes from a more mathematical definition of the term normal, and that means perpendicular to a surface. And the normal force is a surface pushing on something else. Okay, so in the case of the ground, if we have a hill, then the normal force pushes this way. If we have flat ground, then the normal force pushes this way. Okay, always perpendicular to the surface. So in this case, what we have is a car sitting on the ground with gravity pulling down and the normal force pointing back up. So we have the interaction between the earth and the car giving a force that's down, and we have the ground giving the force that's up, and the car isn't moving. It has a velocity that's not changing. So we know that these two forces, they must be equal, because our F equals ma tells us that the sum of the forces, so let's put a little y hat here. Let's pick a coordinate system. So we have minus Fg plus n equals ma in the y direction. But the a is 0, so that equals 0. But now let's make it a little more interesting by adding in you standing behind the car here, pushing on it. Okay? You do this, and you give it a force that points in this direction. Okay? The force of the push. And we can complete our coordinate system here in this 2D example by adding in an x direction. Now, let's remember that we've always been drawing our coordinate systems with orthogonal axes. And the reason that we did that was so that motion in each direction would be independent. So remember that when we were dealing with kinematics, I said that because we have orthogonal axes and our vector equation didn't have any vector products in it, it was actually a system of equations. But if we look back up here at Newton's second law, what do we have? Well, we have a vector equation with no vector products in it. So once again, this equation is a system of equations when we have orthogonal axes. Okay? And you'll notice when we considered the car sitting still, we solved it in the y direction. And in our new example where we're pushing on it, this is perpendicular to the best of my drawing ability, nothing has changed. Okay? We still have this same equation in the y direction. So I have gravity pulling down and the normal force pushing up, and those are all my forces in the y direction. And the forces in the y direction are independent of the forces in the x direction. So the sum of these forces is still 0. And that still tells us that Fg must be equal to n. Okay? But now when I think about the x direction, if I write the same equation, Newton's second law, in the x direction, well, I just have one force now, force Fp in the negative x hat direction, and that's equal to ma in the x direction. So now we see that if we knew the force of the push, our acceleration in the x direction would be minus F sub p over m. And we have, again, independent motion in the x direction. The x direction only cares about the sum of the forces in the x direction. So we have independent influence on each of these axes, and you notice that our acceleration in the end is going to point in the negative x hat direction because our only force points in the negative x hat direction. So our net force points in the negative x hat direction. And this is a property of this equation. Thinking of the net force as a vector, and then looking at the other side of the equation where I just have acceleration, and mass is a scalar quantity, then it turns out that forces, the net force on an object, must cause an acceleration in the same direction as the net force. In fact, this is the reason that we always had gravity only giving vertical accelerations in our kinematic problems, because the force of gravity is always in the vertical direction, and our acceleration will always be in the direction of our net force. So let's take a second to talk about weight versus mass, okay? So weight is the force of gravity on an object. So if we use Newton's second law again, we could say the force of gravity equals mass times acceleration from gravity. But near the surface of the Earth, we know that every object has the same acceleration, right? So we have mg. And we'll eventually get to why this is, but for now it's just a fact that you know. So if all objects near the surface of the Earth have the same acceleration, little g, then we can replace this ag with little g like I've done here, no matter what object we're dealing with. So then Fg equals mg. This is an object's weight. It's the mass times the acceleration that comes from gravity. So an object's weight depends upon its mass. An object's mass is a measure of how much stuff there is. So we can measure an object's mass using its weight because we can measure the force of the attraction between the Earth and the object, and we know what the acceleration from gravity is. So this is what you're doing when you step on a scale and it reads kilograms. Kilograms are a measure of mass, not of weight. And the scale is inferring what your mass must be based on how hard gravity is pulling you into the scale, and then assuming a value for little g. The object's mass is what defines its resistance to having its velocity changed. So the acceleration that an object gets from a force of a given value is dependent on its mass. It's not dependent on its weight. And this concept is called inertia. Inertia is an object's resistance to having its velocity changed. And this is proportional to the object's mass. So the more massive an object is, the more inertia that it has. So greater mass means greater inertia. So your mass doesn't change depending on where you are. You're made up of the same amount of stuff regardless of where you are. Whether you're on the Earth or the Moon, you still have the same amount of stuff making you up. But the force of gravity when you're on the Moon is about 1/6 of what it is on Earth. So your weight on the Moon is about 1/6 of what it would be on Earth. And this is the reason that astronauts look a little like they're floating when they bounce around on the Moon. We said that the force of gravity is your weight, and if this is the force of gravity on Earth, and I know that it's about 1/6 that on the Moon, you can see it if I make this 1/6, well, it still equals ma. But now when I put this 1/6 then, if this was ma on the Earth, okay? So we'll replace it with m times little g. Then to make it the same as the left side here, I would add a 1/6 when I move you to the moon. And you can see, because we know our mass doesn't change, we're made up of the same amount of stuff, whether we're on the Earth or the moon, I end up with m times 1/6 of little g. So that's the acceleration that gravity imparts on you when you're on the moon. And this little tiny acceleration is the reason that astronauts don't return to the ground as fast as they do on the Earth when they jump up on the moon. And that's the reason it kind of looks like they're floating around when they bounce around on the moon. The force of gravity is 1/6 what it would be on Earth. So the acceleration from gravity is 1/6 of what it would be on Earth. So if you push on me and I'm difficult to move, it's not because I'm heavy, but rather it's because I'm massive. It isn't that I'm hard to move because I'm being pulled down into the Earth so hard. I'm hard to move because I have a lot of inertia due to having a lot of mass. And I'm heavy also because I have a lot of mass. Okay? So heavy things are hard to move, but it's because having a lot of mass makes something heavy, and having a lot of mass makes something hard to move. It isn't because being heavy makes something hard to move. So this is an important distinction to keep between mass and weight as we go forward. So keep in mind that mass is a measure of how much stuff is there, and weight is a measure of the force of gravity on an object. So now we come to Newton's third law. And Newton's third law is really simple to state, but it's really important that we fully understand what that statement actually means. So Newton's third law is often stated as, for every action, there is an equal and opposite reaction. But I don't like stating it that way, because it gives the idea that there are these two independent actions and they just happen to occur together all the time, okay? And I don't think that's a good way to think about Newton's third law. So we've actually already stated Newton's third law in the way that I like to state it earlier in the lecture, okay? We did it near the very beginning of the lecture. And I state it like this. Newton's third law is forces are interactions. Okay? Forces are interactions. But what do we take away from this? What am I actually telling you when I tell you this? So the first thing that we should take note of is that an interaction always has two sides, okay? So I have the Earth here, and I have a person, me, and the force of gravity isn't just the Earth pulling me toward the Earth. It's also me pulling the Earth toward me. It's an interaction between me and the Earth. Gravity is me and the Earth being attracted to each other. And this interaction is just one thing, okay? It's the force between the Earth and me. It's one thing, so it can only have one magnitude, Fg. Okay? It's a single interaction, and the strength of the force is the magnitude of that interaction. The key point of Newton's third law is to recognize that a force is a single interaction, and that means that it always has two sides, but with just one magnitude. So in this example, I'm pulling on the Earth just as hard as the Earth is pulling on me. But this seems counterintuitive. When I fall off something, doesn't the Earth just pull me toward it? I can't feel the Earth move when somebody else is jumping up and down. I can't feel the Earth move when somebody jumps off of a high dive, right? And they're in free fall for, say, a couple seconds. So, what gives here? Why does this seem counterintuitive? And we actually have some tools that we can look into this a little bit. We can understand this a little bit more. So, let's look into it a little bit more. Let's say that I have a mass of a nice round 100 kilograms, okay? Then we know what my acceleration toward Earth will be. It'll be little g, right? Just like it always is. So that means I can calculate the magnitude of the force of gravity between me and the Earth. The force of gravity equals my mass times little g equals 980 newtons. But Newton's third law tells us that this is the magnitude of an interaction. So the Earth pulls on me with a force of 980 newtons, and I pull on the Earth with a force of 980 newtons. That's the strength of this interaction. So if we're pulling on each other with this same magnitude, why am I moving a lot and we know that the Earth really isn't moving at all? So let's look at Newton's second law again, okay? If we know Fg, it's this 980 newtons, well, what about if we look at the object of the Earth instead of looking at me? Well, now m, I'll use big M here for the Earth, is different than it was for me. It's not 100 kilograms. The mass of the Earth is 6 times 10 to the 24 kilograms, okay? That's 6 ronograms. And you've probably never even heard the prefix rana before, because 10 to the 27 is such an absurdly large power of 10, right? I had never heard it before. I had to look it up. I don't know what the prefix for 10 to the 27 grams is, okay? But this means that the Earth is 6 million kilograms, okay? That was 4 millions on that. That's 1 million to the 4th power, okay? So 6 million times a million times a million times a million gives me the mass of the Earth in kilograms. And remember, my mass was 100 kilograms, okay? So if I put that mass in for the Earth, and I want to solve for the acceleration of the Earth, then I can see that the acceleration of the Earth is equal to the Earth's mass over the force of gravity, which we calculated up here, right, between me and the Earth, and I get the acceleration that I impart on the Earth. And the acceleration that I give the Earth is 1.6 times 10 to the minus 22 meters per second squared. So now let's go another step further. So if the Earth and I were far enough apart that we were attracted to each other for 5 seconds, okay? So I fell for 5 seconds. Remember that in 5 seconds, in free fall, I would be falling pretty far, okay? So x final, if I started from rest, would be 1/2 g t squared. And if t is 5 seconds, then I fall about 123 meters, okay? And that's about 400 feet. Now, if we do the same thing for the Earth, x final of the Earth, well, in the same equation, I would have 1/2 a of Earth t squared, okay? And if I plug in this number for the a of the Earth, then what I get is that I move the Earth by 2 times 10 to the minus 21 meters. So in 5 seconds of pulling on the Earth, I move it by 2 times 10 to the minus 21 meters. But how far is 10 to the minus 21? Well, the width of an atom, okay, not a molecule, not an H2O, but just the H, okay, one atom. The width is about, or approximately equal to, 10 to the minus 10 meters, okay? So in 5 seconds of pulling on the Earth, I would move the Earth by about 1/100 billionth the width of an atom. Okay? So the Earth and I both pull on each other for 5 seconds. The Earth moves me 400 feet. And during that same period of time, I move the Earth 1/100 billionth the width of a single atom. So this is truly an imperceptible change. So forces are interactions, which means that the truth is you and the Earth pull on each other with the exact same force, okay? You guys pull on each other with the same magnitude of force. And the force has two sides. An interaction always has two sides. There's the side that's the Earth pulling on you, and there's the side that's you pulling on the Earth, okay? So why does it seem like only you move? Well, it's because the Earth has a million times more mass than you do. So when the two of you interact, the Earth's inertia is so huge that you can't move it in any perceptible way, and you just move relative to the Earth. So if we bring this example back to our example of you pushing on the car, Newton's third law is still true. When you push on a car with some force, it's pushing back on your hands with the exact same amount of force, okay? Forces are always interactions. Every force is two-sided in this way. An interaction always has two sides, but with just a single magnitude. So every force is going to involve one object pushing on the other, that object pushing back on the first one in the opposite direction, and because it's an interaction, there's just one magnitude, okay? Both of those directions have the same magnitude. So an equal and opposite force, as it's often stated. So here are Newton's laws, stated in the really simple terms that I usually like to state them in, okay? The first one, an object's velocity changes if and only if there is a net force acting on the object, okay? The second law is the sum of the forces is equal to the mass times the acceleration. And then the third law, forces are interactions, okay? And we know that what we mean by that is that forces always have two sides, the one object pushing on the other, and then the second object in return pushing on the first, and that there's always just one magnitude for this interaction. So we can see that these laws can be stated in a really simple fashion, right? There's barely anything on this page. But we've already seen in this lecture that there's a lot of physics that can come from understanding what these statements really mean, okay? These laws have a lot to say about the world around us. They tell us a lot about the way that it works. And you should remember these for the rest of your life. So how do we put all this stuff to work when we're considering physical systems? Let's consider this block sitting on a ramp that we have over here. Now, we can draw what's called a free body diagram of this block, where we draw all of the forces acting on the object. So we consider so that we can consider the sum of the forces that are acting on the object. Okay? Now, technically, a free body diagram should be drawn with the object that you're concerned with free of its environment. That's why it's called a free body diagram, okay? The body that you're concerned with free of its environment. And then we would draw forces on it like this, okay? But I generally find it more intuitive and a little more useful to draw my forces right onto my picture of the system like we have over here, okay? So that's how I usually do it, and that's how I'm going to show you guys right now. So let's say that our hill here, our ramp, has no friction. So let's think about it as if it's made out of some really slick ice, okay? So what forces are acting on the block? So when we draw the forces onto an object in a free body diagram, we only care about the part of the interaction that deals with forces acting on the block, okay? So for example, we know we have gravity pulling on the block. We don't draw the full interaction, okay, with an arrow in both directions. We're concerned with the block and how it's going to act, so we just draw the earth pulling on the block, okay? So I draw the force of gravity like this. F sub g. Okay? And that's it. That's the earth pulling on the block. So that's the force that's acting on the block. We know that it's an interaction between the block and the earth, but the part of the interaction that acts on the block is just this part, where the earth pulls the block down. Okay? So the earth is pulling the block straight down, but we know that it isn't in free fall, right? The ground is in the way, and the ground pushes back on it. And we said that the ground applies what's called a normal force. And remember that the normal force is always perpendicular to the surface. So in this case, it looks like this, in the direction perpendicular to the ground. And if we don't have friction, that's all the forces that are acting on our block, okay? So what acceleration will the block have? Well, we know that it's going to slide down the hill in this direction, right? So we know it'll have an acceleration in this direction. But how fast will it slide? What will the acceleration be? So we can solve this using Newton's second law. F equals ma. And you should learn to love Newton's second law now, because you're going to use it to death in the next couple of weeks. Okay? We're going to apply it to all kinds of stuff. So here's our system, and remember in our problem solving method, we always draw the thing first. We always list the variables, and right now I'm not going to put numbers on these variables. I don't care what they are. Okay? This is just a general example. But the next thing we always do is we draw a coordinate system. And up until now, I've generally just solved problems by drawing a coordinate system like this, right? X horizontal and Y vertical. Okay? But for this problem, that coordinate system kind of sucks, because A doesn't point in one of those directions, and N doesn't point in one of those directions. So I would have to break both of them down into their vector components to solve this problem. And this is where a clever choice of coordinates is a really good idea, okay? Especially in the future when we start to add friction. So I don't want to use this coordinate system. It sucks. So what coordinate system do I want to use? Well, the coordinate system that is a really good idea, a really clever use, is I take X and I put it along the ramp. And Y, of course, I keep perpendicular to X because I want to have orthogonal coordinates, okay? So that I have independent axes. But when I tip it like this, notice that the acceleration runs right along the X direction, okay? This is really good because now I don't have to use a Pythagorean theorem to calculate the magnitude of the acceleration. It just has a component in the X direction, okay? And by definition, if I make X run along the direction of the surface, well, the normal force is by definition perpendicular to the surface. So the normal force by definition points in the Y direction, okay? So now I don't have to break that one down either. It's pointing straight in the Y direction. And what I'm left with is I just have to break gravity into the X component and the Y component of this new coordinate system, okay? So gravity is still pointing straight down, but I've chosen coordinates that don't point directly in the vertical direction, okay? So now I do have to break gravity down into its components, but in this problem, it's the only force that I have to break down into components, okay? So now to break it up into components, I know that I'm going to have a piece like this that points in the Y direction. So this is FGY. And I'm going to have a piece like this, FGX, that points in the X direction, okay? And if this angle is theta, this is the one we're usually given, the angle above the horizontal. If that one is theta, I can use similar triangles and their properties to figure out that this one is also theta, okay? Now, for the sake of time, I'm going to skip that derivation at the moment, but you should do it yourself and convince yourself that this is true, okay? If this one is theta, then this one in here is also theta, okay? So now, because of the form of our equation here, a vector equation with no vector products, and because of our orthogonal axes, we can now use Newton's second law in each direction independently. So, let's do the y direction first. In the y direction, I have f g sub y, and that's negative because it's pointing down, plus the normal force pointing up in my y direction. And that's equal to m times the acceleration in the y direction. Okay? But if I think about this, I know that the block is just going to move in my x direction that I've defined. It's just going to slide down the hill. It doesn't fly up off the ground, and it doesn't fall down through the ground. So I know that ay is 0. Okay? And in the x direction, I have fg sub x, okay, in the positive x direction down here. It points this way. That's positive x. And in this case, with no friction, that's my only force, right? And that must be equal to the mass times the acceleration in the x direction. But a points directly along the x direction in this example, so I don't even need the subscript. I can just say it's ma. And now if I want to know what a is for this no friction example, I now have f g sub x over m. And it's really that simple. It's in the x direction, okay? Right? Because fg sub x, remember, f sub g is mg. And then the x component here, you can see I have my angle here. The x component in this case is across the right triangle from theta, so it must be sine, right? The one that's opposite the angle is sine, so it's mg sine theta over m, okay? And then I get g sine theta, okay? So in the end, with no friction like this, my a doesn't actually depend on the mass of the sliding object. And this is actually a significant finding. We would think that a heavier object would slide down the hill faster, but with no friction involved, this is really slick ice. In the real world, we never have no friction. But maybe if the ice was really, really slick, we have something that's close. The mass doesn't actually matter. How heavy the object is doesn't actually matter, okay? And the way we can think of this is you can think that the normal force is pushing the block back up, so it doesn't free fall, right? It's not, a isn't just little g. It's not the same speed that it would fall if there was no ground there. But the normal force doesn't push perfectly back up. And so in the end, what it does is it only cancels a little bit of g. So just like in free fall, where all of our objects have the same acceleration, when they're sliding down a hill with no friction, the normal force cancels some portion of the acceleration that it would have if it was in free fall, and then pushes it down the hill with some fraction of the free fall acceleration. So let's look at some common sources of force in this class, okay? We'll see forces that come from a number of different things in the class, but these are a few that just come up very often, okay? So note that in this list, what is not here is MA. There is no MA force. MA is what happens when there is a net force. It's a vector that's equivalent to the net force, but it is not actually a force of its own. Okay? So keep that in mind as we solve problems in this class. MA is a vector that's equivalent to net force, but it's not actually a force of its own. So gravity is the first one. Gravity is an object's weight, right? Fg equals m times little g. And this drives a lot of interesting systems. So this one's going to come up repeatedly. Okay, we're going to use this one all the time, and we're always going to be concerned with this one. The normal force, remember, is the force of an object pushing against something. And it's always perpendicular to the surface of the object. So in the case of, say, the ground or a ramp or something that's inclined like this, the normal force is always perpendicular to the surface of the ramp. Okay? The next one is tension. And tension is applied by a force pulling on a rope or a string or a cable or something like that. So if I have a block and I have something attached to it and I pull on this thing, okay, so this is my rope, and then I pull on it with a force P, okay, just the force of some pull. So if my rope doesn't have mass and my rope doesn't stretch or deform in any way, then the force that I apply to the one end of the rope will end up being the force that's applied to the block, okay? And generally in this class, when we deal with, tension, strings and ropes and things like that, we're going to go ahead and approximate that they don't stretch, they don't deform, and that they have no mass, okay? They're going to be an ideal rope. And then the last one that I want to mention here is springs, okay? And a spring applies a force when it's compressed or when it's stretched, okay? And we'll see springs come up a little bit now and a lot more later in the class when we discuss some other concepts, okay? So if I have a block on a spring and I press it back so the spring is displaced some amount, x, then the spring will apply a force, and it'll apply a force that presses in this direction, okay? The force of the spring. And that's all the material that I wanted to cover today. So we had a lot of material today, and you'll have a lot of reading to cover this same material in the voice and in the explanations of the author of your book, okay? But these things are things that we're going to look at in more depth as the class continues, and we'll do a lot more examples that will help you get a better handle on these things. And the things that are covered today are some of the most fundamental aspects for understanding physics. And these properties and their implications give us some really powerful tools for understanding the world around us.